Okay, this problem was posted over 10 years ago, but one of my students stumbled upon it and asked me to help with it. Make the observation that there was a comment to this post that indicated what the cone looked like, the tank. It was a cone 12 feet high and with a radius of 5 feet. You need to know for work that we're going to move a wafer of water, this red strip, a distance of, well, however far it is to get it over the top of the tank. So we've set up this coordinate system with the vertex of the tank down here at 0, 0. This upper right-hand corner at 512. That allows us to figure out the equation of this side right here using slope-intercept. Y equals 12/5 x. You could solve this for x to get the radius of this wafer of water. You could also do it using proportional right triangles, similar right triangles. 5 is to 12 as x is to y, x equals 5/12 y. So that's the radius of this wafer right here. And to get the volume of that wafer, we're going to use pi r squared h, where h is going to be a change in y, dy. So here's the volume for a typical wafer right there. Pi r squared h is delta y. You need to know that the weight of water is about 62.5 pounds per cubic feet. This volume is in cubic feet. So the weight of that wafer of water is the volume times 62.5, and that'll be pounds, because the cubic feet cancel out. The distance the wafer of water is moved has to be from, well, we want them, if it was way down here, this distance would still be y, so we'd have to move it 12, take away this y. And that's true for any of these wafers. 12, take away however high the wafer is above the origin. So the work to empty a full tank, empty the entire tank, would be, well, these wafers occur from y equals 0 to y equals 12. And the distance each wafer is moved is 12 minus y. And work is weight times distance. So there's your definite integral to move them all of the water out. Now I'm assuming that this, to pump 4 feet of water out over the top, means reduce the height of water by 4 feet. So in part A, when the tank is full, if we move 4 feet of water, that's this section of water right here, this body of water above that red wafer, which is at a height of 8. And so the definite integral, instead of going from 0 to 12, the wafers only occur from 8 to 12, 4 feet. So here's what that looks like. Here's the work for, again, all of the water. Here's the definite integral with all the constants moved out front. And then for part A, 4 feet of water when the tank is full, 8 to 12. And the only change for part B is if there's only 4 feet of water in the tank, that water occurs at the bottom of the tank. Right here is the water, 4 feet of it. And we want to move all of that water out over the top. So those wafers of water occur from 0 to 4. By the way, here's how we evaluate the definite integral excluding this constant that was out front. Distribute the y squared, find an antiderivative, evaluate for all of the water 0 to 12. If you want to do from 8 to 12, then we'd have to be subtracting what would happen if we put 8 in to this antiderivative. So it would be from 8 to 12. And 0 to 4 for part B. Okay, there you go. Hope that helped. If you have any questions, post a comment. By the way, this is foot-pounds because the volume of water is in pounds and we're moving it some number of feet each wafer.